For centuries, whenever people imagined the absolute smallest piece of matter in the universe, they pictured something a lot like this: a tiny, solid, unbreakable marble. They called it the atom, which literally translates to indivisible. By the late 1800s, this idea of the solid marble began to crack. Experiments by scientists like J.J. Thomson revealed that atoms were composed of even smaller internal pieces, negative electrons and positive protons. But those two pieces left a mathematical puzzle. If you weighed an atom, the protons and electrons didn't add up to the total mass. There was a large amount of weight missing. In 1932, a physicist named James Chadwick solved the equation by discovering a third piece inside the atom. It was heavy, but it carried no electrical charge at all, so he named it the neutron. With the electron, the proton, and the neutron identified, science had finally identified the three basic building blocks of all matter. The next challenge was figuring out how they actually fit together. This hand-drawn diagram illustrates J.J. Thomson's best guess at the time. He proposed that the atom was a giant sphere of positive energy, and the negative electrons were stuck inside of it, sort of like seeds suspended inside a watermelon. A few years later, Ernest Rutherford decided to test the watermelon idea. He fired a beam of fast-moving positive particles at an incredibly thin sheet of gold foil. Because the foil was thin, he expected his particle beam to punch straight through the gold atoms like bullets through tissue paper. Look at what actually happened in this animation. Most particles passed right through, but a very small number violently bounced backward. Rutherford realized protons and neutrons are tightly packed into a dense central core, the nucleus. Niels Bohr then suggested electrons travel in fixed lanes around this center, exactly like planets orbiting the sun. Bohr's solar system is the picture of the atom most of us grew up with, but physicist Werner Heisenberg proved that electrons move way too fast to follow neat, rigid paths. In fact, if you know an electron's exact speed, it is mathematically impossible to know its exact location at the same time. They behave more like fuzzy waves of energy than solid planets. So the modern atom is not a clean solar system. It is a dense central core surrounded by three-dimensional probability clouds. The electrons are flying around at high speeds, building a complex, layered, microscopic city. Even in a cloud of probability, we can still locate where an electron is most likely to be. Physicists use 4 quantum numbers. Think of these exactly like a mailing address used to deliver a letter: state, city, street, and house. The first is the principal number, or n. This is your state. It tells us how far away the electron's main shell is from the central nucleus. The second number, L, is your city. It dictates the actual geometric shape of the space the electron lives in. The third is the magnetic number, M. This is your street name. It tells us exactly which direction that shape points in three-dimensional space. Finally, we have the spin number, S. This is the specific house. It simply tells us if the electron is spinning upwards or downwards. This notebook sketch shows the city shapes. S orbitals are round spheres, while p orbitals look like dumbbells pointing along 3 axes. Further down, d orbitals stretch into complex cloverleaf patterns to accommodate more electrons. It helps to remember that these odd shapes are not physical containers made of matter. They are mathematical boundaries. They just outline the specific rooms where the rules of physics allow an electron to exist. So how do electrons choose which of those rooms to move into? This handwritten chart maps out the first rule, the Aufbau principle. Electrons are naturally lazy. They will always fill the lowest energy rooms closest to the nucleus first, starting at the 1s level, before moving up to higher, more energetic levels. Once inside a room, they follow the Pauli exclusion principle. This law states that a single orbital room can hold a maximum of 2 electrons, and if they share that room, they have to spin in opposite directions to avoid repelling each other. Watch how they fill a larger floor in this animation. This demonstrates Hund's rule. Electrons behave exactly like strangers getting on a bus. They will always spread out and claim their own empty seat first, and will only start sitting next to each other once every room has at least one occupant. They seek low energy, demand opposite spins, and prefer personal space. By following these strict behaviors, electrons arrange themselves predictably, dictating the chemical properties of every single element in the universe. When you put the address system and the filling rules together, you get an electronic configuration. This line of notes shows the map for nitrogen. With just a glance, you can see how all the information about an atom's structure is compressed into a single line. The large number is the shell level, or the floor of the building. The letter tells you the shape of the room, whether it's a simple sphere or a dumbbell. And the small superscript number tells you exactly how many electrons are currently living in that room. This journey shows how our understanding has evolved from imagining atoms as solid billiard balls to seeing them as complex quantum cities. Today, we know the atom is a system defined by energy levels and three-dimensional clouds, where every tiny particle has its own specific place.